The next unit will primarily be focusing on the usage of Laplace transforms. So obviously first we're going to learn what they are. The application of the Laplace transforms will come later on once we know how to work with them. Before we define the Laplace transform, just kind of look at a few things that you've learned along the way. In Calc 1, you mainly did, well, two things. You took derivatives of functions, and you also integrated functions. And the result, after doing the derivative or integral, was some new function. Here in this case it would be 8x. Here it's 1/2 x squared plus some constant. Okay. So the idea here is that these operations transformed a function into a new one. The other big deal here is that whether you're doing derivatives or integrals, you guys already know this, but they all possess or have the linearity property. Which again means that if you are taking the derivative of some linear combination of functions, that you would just apply the derivative to each function and distribute the idea. So here you would get a times the derivative of f plus b times the derivative of g. And similarly with integrals, if you integrate a linear combination of functions, you get a times the integral of f of x plus b times the integral of g of x. And you have your constant. Okay, so all along in calc, you've been transforming functions into something new. Now, particularly, let's go ahead and fast forward to first semester in Calc 3. So this is the other day out of the three that we mentioned, Calc 3. We computed integrals such as this. Let's say 2x y squared dx. Let's go from 1 to 2. And I'm sure everyone remembers how to do that, right? What would the integral of 2xy squared become? And then this is from x equals 1 to x equals 2. So we get 4y squared minus y squared, very good, for a grand total of 3y squared. Okay, so in particular, this operation transformed a function into one new variable. Mainly now it's just in terms of y. Okay, so now if we generalize this idea, let's say we have an integral from a to b of some function k of st times f of t dt. This would transform whatever we have going on in here into a function in terms of what? Very good. So we integrate with respect to one of the variables. Naturally, we're going to end up with a completely new function that now only has the other variable as its main variable. Okay? These are the integrals that we're interested in. Okay? This type of integral is called an integral transform. Oops. And we will work with the assumption that the interval of validity here is going to be just from 0 to infinity. So now, adding. Here's a definition. If f of t is defined for t greater than or equal to 0, then the improper integral from 0 to infinity of this integrand that we mentioned earlier, k of st f of t dt, you evaluated a few of these in Calc 1. What do we have to do to figure it out? So let's say b goes to infinity. We'll go from 0 to b, and then we just repeat the function. Okay. If the limit exists, we say the integral is convergent, and therefore the integral itself exists. If the limit does not exist, the integral does what? Or is good, divergent. Okay, so this is all just kind of a crash course on improper integrals. we combine the idea from Calc 1 with now multivariable integrals, which is what we dealt with in Calc 3, and we get to our definition. If we let this mysterious k of st function be defined as e to the minus st, now we get the definition for the Laplace transform. And that is, the notation is like kind of like a script L. Okay, so when you see this fancy looking L, we're talking about taking the Laplace transform of a function. Then we use braces to indicate which function we are taking the Laplace transform of. And the definition for it is exactly what we led up to. We take the improper integral from 0 to infinity of e to the minus st f of t dt. And again, the assumptions here are that t is greater than or equal to 0, and the integral converges. Okay. Questions so far? If you came in late, you can kind of review this later on your own, but the main idea is just to know that we're studying this new weird-looking function called the Laplace transform, and the definition of it, or to compute it, you'd have to evaluate this improper integral. Okay, so we'll do a couple of those. Let's clear up just some notational issues. In your work and in my notes and in the book, a lowercase f or g or whatever letter we decide, that's always going to indicate the function to transform. If it is capitalized, that means that it already has been transformed. So it's the result. It's the result of the Laplace transform of f. Okay? So a lot of the definitions and things like that, we will be using capitals and lowercase. So just kind of know that going forward, it will make life a lot easier going on. Okay. Let's do a quick example and then talk about some of the properties that we need to get really comfortable with moving forward. We'll start off nice and easy. Let's say we want to evaluate the Laplace transform of 3. In order to do that, we'd have to do the integral of 0 to infinity of what? Good. Which is the same as 3 times the integral from 0 to infinity e to the minus st dt. And now, using the limit idea, let's say this integral, when I integrate e to the minus st, I get minus 1 over s e to the minus st. But now let's use that b. So we're going to do the limit as b goes to infinity. As t goes from 0 to b. So 3 times the limit as b goes to infinity of, if I plug in the bounds, minus 1 over s e to the negative bs minus negative 1 over s times e to the 0, which is just 1. So if I take the limit as b goes to infinity of this term here, what do we get there? That's just 0. Good. And as b goes to infinity of positive 1 over s, well, there's no b there, so we just get 1 over s. So our answer, as we take the limit, we get 1 over s of the entire function. So 3 over s would be the result of the Laplace transform of 3. Does that calculation, and I know you're probably wondering, well, why, where the differential equations go, right? We're not talking about diffie q anymore, but we will get there. Right now it's just a matter of understanding what the definition is, how to calculate it, and we'll eventually apply it. Make sense so far? Okay. Now that we've done what I call more official notation, you'll see me be very lazy, and so will the textbook, which I actually kind of like. You don't have to evaluate these integrals with limits every time. Okay, so we're going to go ahead and say that the limit as b goes to infinity of e to the minus st of s, for example, over s, for example, evaluated from t equals 0 to b, is equivalent to just saying e to the minus st over s as t goes from 0 to infinity. So it's understood. It's understood that even though this isn't quite proper to do, that this is essentially what we're doing. Does that make sense? So we don't have to keep writing out all these limit calculations. Okay. And naturally, as e to the minus st, well, as t goes to infinity, e to the minus st approaches 0 when t goes to infinity. Or maybe I should say that the other way around. When t goes to infinity, as t approaches infinity, e to the minus st approaches 0. Okay, so these are the assumptions that we're going to work with moving forward. Okay? All right. So we'll come back and do another calculation today if we have time. We're probably not going to finish the section today, but we do have to go over some very big ideas as far as properties and things go with these transforms. So first, let's kind of talk about the idea that just like integrals and derivatives possess linearity, so does our friend the Laplace transform. This is why it's called a linear transform. Or operator. So just like with ddx and integrals, if you apply the Laplace transform to a linear combination of functions, a f of t plus b g of t, you would do exactly what you think you should do, which is to compute what? With integrals and derivatives, what did we do with the constants? Mm-hmm. Good. And now, using our notation from earlier, what happens with the notation here? After we take the Laplace transform of little f, we get big F. And notice, every time we do this, what variable do we end up with? S. Okay. Oh, geez. I was about to write Laplace transform again. So this is the same as A times capital F of S plus B times capital G of S. Now, obviously we're going to be interested in functions that primarily have Laplace transforms. Not every function does necessarily. So let's talk about some conditions for existence. Okay, 1, f, so the function that we are transforming must be piecewise continuous on the interval from 0 to infinity. And all that means is that we are allowed to have piecewise defined function. So something like this would be okay, and so on and so forth. Okay, so piecewise defined functions are good. Naturally, if we have one big interval from 0 to infinity, that's fine, but we could also subdivide it into smaller intervals if we want. Okay, so as long as we have that condition met, that's good. And then the last one, which we'll define here in a minute, is that f must be of exponential order for little t greater than big T. So hopefully you're wondering, well, what does exponential order mean? Here you go. The definition for exponential order is as follows. A function f is said to be of exponential order. If there exist numbers, we'll say little c and big M, both greater than 0, and a t greater than 0, such that the function that we are taking the Laplace transform of, if we were to take the absolute value of that function, at some point it will always be less than an exponential function, say me to the ct. And what we mean by some point is that it does not always have to be, but there's got to be some breaking point, which is what we mean by little t greater than t. Okay, so would a picture help with this? Okay. So here's your little t axis. Here's our breaking point, capital T. Let's say this is little f of t. Okay, so it's generally an increasing function. The idea is that in order for this function to be of exponential order, that we're able to find some exponential function where the exponential function basically overrides or takes over and becomes bigger than f of t. So maybe it starts out smaller, but then right when we hit that breaking point, now it's clear. Now it's clear that this function here, me to the ct, is going to be greater than or equal to f of t. Okay, so this is what we mean for a function to be of exponential order. Yes? Yes. Well, not always, but at some point and then thereon after, it will always be beaten by an exponential function. Yes. Okay. Here are some easy examples to comprehend. And I want you guys to tell me what the breaking point is. F of t equal to t. F of t equal to sine t. Even cosine. These are all of exponential order. If you think of their graphs, you know, there's t, here's sine, here's cosine. I probably messed that up, but work with me here. And here's your exponential function. Yes?
Does it have to be greater than
After a certain point, yes.
so we
Yes, it could have been here. Yep. So it could have been, and actually in this case, if we do just plain old e to the t, it would be, right? So this is a better example. So we say that these are all of exponential order for what value of t? So when t is greater than 0, right, the exponential function is larger than t, sine, cosine, and there's a plethora of others, but this is just to give you an idea of what it looks like graphically. Okay. Now in comparison, f of t equals e to the t to the fourth would not be of exponential order. And you can spend a lot of time on your graphing calculator trying to figure out if it ever does get overtaken by a normal exponential function. But hopefully you understand that if we're comparing e to the t to the 4 with some exponential function me to the ct, why is this not of exponential order? Yeah, and a fourth degree in general, here we have a fourth degree exponent, and this is just a plain old linear exponent, right? If this exponent is larger than that one in general, then this function will be larger than this function in general, and therefore it's not of exponential order. Okay? Will polynomials always be of exponential order? Exponential functions will always overtake polynomials, right? You'll always find that it might be way on down the road, but at some point it will have that breaking point. Okay. I think we can finish with a little theorem and a proof, and we'll call it a day. Let f of t be piecewise continuous on the interval from 0 to infinity, and also of exponential order for some t greater than capital T. We're going to go ahead and prove that these two conditions suffice for existence. So then the Laplace transform of f of t exists, and we'll say for some value s greater than c. Right, so this shouldn't be too bad to get through. If we are to prove that these two conditions are good enough, then we'll just go ahead and start with what the definition for the Laplace transform is, and see if from there we can arrive at what we need to have. So the definition for the Laplace transform is the improper integral from 0 to infinity of e to the minus st f of t dt. And now, using the fact that f of t is piecewise continuous, we have several pieces. Let's call this interval I1. And then maybe from here on after, Let's call this interval I2. Clearly, if we look at the way we've split up I1, no matter what you do, there will always be some exponential function greater than a little snippet of a function, yes? So what we're going to do is, well, oh, this will be a big, sorry. Let's call this right here t. Okay, so that's going to be our breaking point. Our job is going to be to find some point t that we have an exponential function that's going to be greater than f of t with just these two conditions, that it's of exponential order and that it's piecewise continuous. So if using the definition, we can compute the integral from 0 to t of e to the minus st f of t dt. So this would just be let's call this a. So if I were to take the area under each of these, let's call that area A. Okay? We can split up this transform into as many little pieces as we need, right? If there's 5 integrals, 6 integrals, doesn't matter. We can split it up and add up all the parts. So this part will be just A. And now the other piece is this one over here. So that's the second half. That'll be plus the integral from what to what? T to infinity e to the minus st f of t dt. Okay, and we're going to call that b. Okay, so we know A exists. Because it's not an improper integral. We might have several integrals to compute, but this is not a big deal. So A, the first part of this calculation is trivial. B exists. That's the next thing we need to do. Now, here's why. If we take a look on the interval I2, starting with the integral from t to infinity, let's take the absolute value of e to the minus st f of t dt. And now we're using the assumption that this function, right when we hit t, there's some exponential function that's greater than that. Okay, so because it's of exponential order, the definition says that this should be less than or equal to, I'll pull out the constant, but e to the minus st, and it becomes e to the ct dt. So we're just using the exponential order idea. Naturally, if this function is larger than this one, when we take the integrals, the area for this one is going to be larger than this one. Okay? So now if we go ahead and compute, working with the red part here, I'm going to factor out a t from the exponents here, so then I get c minus s. So that then this becomes a little easier. Unit circle quiz. That's fine. I'll write on the back of it. Okay, so here we are. We've cleaned up the integrand a little bit. If we factor out the t, it looks a little nicer. If I integrate, what do I get? Keeping in mind this is with respect to t. I'll do the hard part. What's the integral of an exponential? Good. And now we're going to go ahead and go from t equals capital T to t equals infinity. Again, where we understand that what we're really doing is evaluating the limit as we go to infinity. So now if I plug in infinity, or I take the limit, what happens? Why? Thank you. So this part is actually negative, since s is greater than c. So when you do the limit as t goes to infinity, this becomes a negative exponent, so this goes to 0. So then all that's left is the second part, which is just minus m over c minus s. And now we just plug in capital T into t. So we have an actual value for this, which means that the integral converges. And if this integral converges, since the integral from t to infinity of e to the minus st f of t dt was less than the one that we just computed, which I'll just write down again. If this converges, then this also converges. Why? Yeah, it's called the comparison test. Good. And therefore, not only did A exist, but the second half of the calculation B also exists. And therefore, the Laplace transform of f of t also exists. Uh-oh. Please still be recording. Okay, good. All right, that's it. Sorry. I know I kept you a couple minutes extra today. That's a good place to stop. We're only going to deal with these kinds of Laplace transforms. So they're going to exist. The calculations at first are going to be pretty intensive, but of course,